Welcome to the talk on Learn Disentangled Latent Representations for Scalable Image Coding for Humans and Machines. My name is Matino Huck, and this is a joint work done with Ezgi Ozilkan, Yomin Choi, and Fabien Racapé at Interdigital. We will start by introducing scalable image compression, as well as discussing related works. Then we will showcase the proposed framework and architecture, and then after that we will look at the experiments and results. Next, we will look at how information is distributed across the latent variables, and finally we will end with concluding remarks and ideas for possible future work. This diagram provides an interpretation of a traditional image compression codec, such as JPEG. The input image X is fed into an encoder-side invertible transform, such as DCT. Then, the result U in the transform domain is quantized and losslessly entropy coded. The quantized U hat is then fed into the decoder side inverse transform, which generates the reconstructed image X hat. Finally, to assess the performance of this codec, we may compute the distortion between the original image X and the lossily reconstructed image X hat. Additionally, we may measure the rate as the length of the bit stream outputted by the lossless entropy coder. Now we move on to nonlinear transform coding via artificial neural networks. This time, the input image X is fed into GA, which is an encoder-side nonlinear transform with learnable parameters theta. Then, the result U in the transform domain is once again quantized and losslessly entropy coded. The quantized U hat is then fed into GS, which is a decoder-side nonlinear transform with learnable parameters phi. This outputs the reconstructed image X hat. Finally, to assess the performance of this codec, we may again compute the distortion between the original image X and the lossily reconstructed image X hat using some differentiable metric such as MSE or MSSIM. The rate may also be computed in a differentiable manner. In multitask image coding, we may divide the transform domain latent space into multiple parts. This is often referred to in the literature as VCM, or video coding for machines. The first part of the latent space may be allocated to a machine task such as segmentation or object detection. The second part of this latent space may be additionally used for a second task such as input reconstruction. This technique leads to improvements in the bitrate for the specialized machine tasks without sacrificing accuracy. In scalable image compression, the bit stream derived from an input image is partitioned into various parts. The base bit stream is a small part of this bit stream that we use for the computer vision task. The enhancement bit stream is a larger portion that provides additional information that may be used for a more information-heavy task, such as image reconstruction for humans. We will now look at some prior works in this area of learned scalable image compression for humans and machines. In the diagrams are various compression encoder architecture designs. In each of these, the input image X is fed into an encoder in order to generate bit streams. These are highlighted in pink. Figure A shows the model architecture which is used by Shamain et al. The base bit stream S is derived from X. This base bit stream is then used to produce X tilde, which is a first approximation attempt at reconstructing the original input image, X. The difference between X and X tilde is called the residual, which is labeled as R in the diagram. This R is then transmitted as an enhancement bit stream, which can be used for reconstructing a better quality version of X. Figure B shows the architecture used by Choi et al. This time, the entire bit stream is directly outputted by a single encoder, which partitions the bit stream into two parts, the base Y1 and the enhancement Y2. An additional latent space transform is used to generate S, which are latent features that are compatible with some existing pre-trained machine task model. In Figure C, we propose an architecture where the desired machine task features S are given to the encoder in order to generate the base bit stream Y1. We claim that this leads to reductions in the base machine task bit rate since the learned model is now made directly aware of the desired outputs. In comparison with Figure B, which indirectly attempts to learn the target output, our design features an encoder which has access to both of the desired outputs, both X and S. This model architecture diagram is taken from the prior work Choi et al. It provides a more detailed look at the specifics of their design. To reiterate, we note that y1 and y2, which are highlighted in pink, are used to derive the outputs x hat and s hat. S hat, which is highlighted in blue, is generated directly from y1 by applying a latent space transform, which helps ensure compatibility with the input to the computer vision backend model. However, we note one possible issue with this architecture design. Because of the arbitrary latent space transform, the model may learn a representation, y1, that contains more information than is necessary for reconstructing S hat. In particular, y1 may contain information that is only useful to the second image reconstruction task. Our proposed approach attempts to address this issue by providing further encouragement to the model in order to produce a more compact y1 that is machine task specialized, thus ensuring that any additional information is allocated to the enhancement latent y2 instead. We now introduce an approach based on variational inference that attempts to produce disentangled latent spaces for y1 and y2 given two random variables x and s as an input. We model p theta as a joint probability distribution of x, s, y1, and y2. First, we apply the chain rule for joint probability distributions. Then, for the next line, we consult our graphical model. By our diagram, we may assert that y1 and y2 are independent. This property will allow us to entropy code them separately. We also determined that S is conditionally independent of y2 given y1. Using these observations, we are able to eliminate the dependencies on various variables. The data likelihood may be determined by integrating the above probability distribution over y1 and y2. Unfortunately, the resulting integral is intractable. In order to overcome intractability, we may introduce a variational posterior q-phi instead, as is commonly done in variational Bayesian methods. Our model imposes a factorization between y1 and y2 based on dependencies within the model inputs x and s, which are treated as individual random variables. In order to compute the loss function, we may simply minimize the Kullback-Leibler divergence between q and p in a manner similar to Palais et al. We seek to minimize the value of the KL divergence between Q and P. We may take the average or expectation of this quantity or the dataset for x and s and set this to be our loss function. By expanding the KL divergence, we obtain the next line where the first two terms in the expectation are 0 and the remaining terms represent the distortions for x and s as well as the rates for y1 and y2. In order to tune these terms independently, we may introduce additional hyperparameters such as the lambda and gamma factors that we have imposed upon the distortions. Our proposed architecture is shown here. In our approach, the front half of the machine task vision model is directly integrated into the compression model in order to generate the features S. This helps the model create a bit stream that is more optimized for the machine vision task. We also resize the input x before concatenating it with s in order to feed it into a transform that generates the base latent y1. This provides the transform with a more informative set of features with which to generate an easily compressible base latent y1. On the decoder side, the reconstructed features s hat are fed into the back half of the machine vision task model in order to generate the predicted labels t hat. Our encoder and decoder are comprised of two learned transforms each, for a total of 4 transforms. The encoder side transforms and their layer configurations are highlighted in pink. The decoder side transforms and their layer configurations are highlighted in blue. We use a layer configuration similar to the hyperprior models introduced by Palais et al. There are minor differences in the number of channels where it is necessary due to the multiple tasks and multiple bit streams. The number of channels in the latents y1 and y2 are denoted by M1 and M2 respectively. We test for a variety of configurations for M1 and M2 as will be shown later. In our experiments, we tested various configurations of hyperparameters for the number of channels in the transform domain. We trained our models on the Vimeo 90K dataset, where the distortion terms within the loss function were computed using mean squared error. We evaluated object detection performance on the COCO 2014 validation dataset using the mean average precision metric for an intersection over union threshold of 0.5. We evaluated input reconstruction performance on the codec dataset for both MSE and MS-SSIM. We also benchmarked the performance in comparison with standard codecs such as HEVC, VVC, as well as a comparative model without pixel CNN-style autoregression from Choi et al. Note that the standard codecs do not support machine vision task scalability, so their performance tests are done assuming a single task setup. These are the results of our experiments. Figure A shows the object detection accuracy versus bitrate performance of all the codecs we tested. The baseline accuracy model is 55.8%. The horizontal dotted line represents a 2% lowered point of reference from that baseline. As shown, our model with all tested configurations achieves a reference accuracy at just over 0.3 bits per pixel. The other tested codecs, including Choi et al., HEVC, and VVC, all require at least 0.6 bits per pixel in order to achieve the reference accuracy. Figure B shows the image reconstruction performance as PSNR versus BPP. Here, our model shows a reduction in performance compared to the other codecs. However, as shown in Figure C, when measured in terms of MS-SSIM, our image reconstruction performance is competitive with HEVC. This diagram visualizes the relationships between entropy, conditional entropy, and mutual information. The entire red circle represents the rate cost of the base bit stream y1 and is labeled as h of y1. The entire blue circle represents the rate cost of the enhancement bit stream y2 and is labeled as h of y2. The region where the circles overlap represents information that is present in both bit streams. However, since we are coding both bit streams using disjoint entropy models, it is not in our interest for there to be any overlap in the circles, since this would represent bits wasted by encoding the same information twice. The part of the blue circle that does not overlap with the red circle is the conditional entropy of y2 given y1. This can be thought of as the rate cost of the enhancement bit stream given knowledge of the base bit stream when coded using an ideal codec. The total shaded area is the joint entropy, which represents the total bitrate cost using an ideal codec that can code the overlapping region with no additional rate costs. These diagrams demonstrate how redundancy in information affects the total rate cost. The first diagram contains redundancy in the bit streams due to the overlap in information. For an ideal codec, the total shaded area will be the rate cost. However, in practice, codecs such as ours may require the bit streams to be coded using disjoint entropy models. Thus, the actual rate cost is the sum of the area of each individual circle. In the second diagram, the bit streams are fully disentangled while maintaining the same shaded area. Thus, an ideal codec which is capable of coding the overlapping regions with no additional rate cost, and a codec such as ours, is able to code the disentangled bit streams with the exact same efficiency. That is, the actual rate cost now matches the shaded area representing the total amount of information. The bit rates of our scalable codec versus Choi et al.'s codec are tabulated on the left. These were all measured at a 2% loss threshold in mean average precision for consistency. We define a metric for measuring redundancy as the fraction of the bit stream yj that is contained in another bit stream yi. This is sometimes also known as the uncertainty coefficient or proficiency. Based on the tabulated values, we establish the bounds on redundancy in the enhancement bit stream as shown. Under the tested configuration, we estimate that ours has a tighter upper bound on redundancy. This figure shows the feature map of the latents y1 and y2 for both our scalable models and Choi et al.'s derived from the given input image. The top 8 channels of each latent are displayed in terms of their bitrate cost, and they are sorted in descending order. That is, the channels to the left have the highest bitrate cost under the respective entropy models. Notice that in our model, the base latent y1 is specialized with the machine vision task and contains less image-like structures that would be relevant to humans. That information is instead allocated within the enhancement latent y2, which is intended for human vision. Conversely, the configuration we tested for Choi et al. Shows the opposite. Y1 contains more information that is not relevant to the machine task. Thus, our model shows better specialization to the machine task. In conclusion, we presented a learned image codec with a new variational formulation, which offers latent space scalability for human and machine vision tasks and provides a new way of disentangling the learned latent representations. Our codec shows significant reductions in bitrate at the base layer in comparison with existing scalable codecs. However, this scalable paradigm still needs further investigation in the future on how to improve the reconstruction task performance while maintaining the same analytics task performance that our codec attains. Thank you for listening to this presentation.